Stable systems, fragile edges. A system that runs smoothly most days can still be one bad day away from behaving strangely. Automation makes that contrast sharper. Quiet stability in the center and sudden instability at the edges. When automation is optimized for stability under yesterday's conditions, it tends to convert change into disproportionate failure because it learns the typical case as a rule and treats the edge case as noise. Automation is built under constraints, limited data, limited time, limited compute, and limited tolerance for complexity in design and operations. Those constraints force choices about what to model and what to ignore, and the easiest thing to ignore is what rarely happens. A stable environment rewards this ignoring. The measured performance rises, the variance falls, and the system appears reliable. The mechanism is not mysterious, it is a trade-off. Every automated control system trains adaptability for efficiency. If it is tuned tightly for a narrow range of inputs, it can be fast, cheap, and predictable. If it is tuned loosely to accommodate novelty, it becomes slower, more expensive, and harder to validate. Stability invites tight tuning, because tight tuning wins the metrics used to justify the system. Incentives then complete the shape. Teams and organizations are typically rewarded for minimizing visible errors, meeting service targets, reducing cost, and increasing throughput. Edge case resilience is rarely a primary metric because it is harder to demonstrate, harder to measure, and often looks like unused capacity. This produces a feedback loop. Success under normal conditions leads to more reliance on the automation. More reliance reduces human practice in handling exceptions. Reduced practice makes exceptions more damaging. The damage then motivates even more automation to prevent recurrence, often by narrowing the operating envelope further. Consider generic examples. A scheduling system allocates resources based on average demand. Under stable patterns, it produces excellent utilization. But when demand shifts suddenly, it may keep optimizing against an outdated forecast, amplifying shortages because its objective function still penalizes idle capacity more than it penalizes missed service. Or a quality filter is trained to reject common defects, it becomes efficient at the known failure modes. When a new defect appears, the filter may classify it as acceptable because it resembles the non-defective class more than the historic defect class, and the system's stability, its confidence, becomes the very channel through which error spreads. These failures are not only technical, they are measurement failures. Automation is guided by proxies, latency, utilization, accuracy on a test set, error rates within a known distribution. The proxy loses contact with the underlying goal. The system keeps optimizing, but it optimizes the wrong surface. That is the quiet failure mode, not a crash, but a disciplined, repeated production of the wrong outcome. Finally, stability itself can become a trap. If the automation reduces variability, it reduces the signal that conditions are changing. Anomalies get smoothed, alerts get tuned down, and the early warnings that would have prompted adaptation are treated as false positives. In a stable regime, that tuning looks prudent. In a changing regime, it delays recognition until the boundary is crossed and the error becomes structural rather than incidental. This is where human values enter, because what gets automated is what gets attended to, and what gets attended to becomes what is treated as real. When stability is the prized output, attention narrows toward keeping dashboards green and variance low. Responsibility can then drift. The system decides, the metric speaks, and the human role becomes maintenance of the pipeline rather than judgment about the environment. Meaning erodes in a specific way. Work becomes the management of exceptions rather than the understanding of purpose. Yet exceptions are also where reality announces itself. If edge cases are treated as noise, then reality's messages are discounted precisely when they are most informative. The second-order effect is cultural. People become skilled at operating within the assumed conditions, and less skilled at noticing when the assumptions have expired. Changing conditions are not merely rare events, they are the ordinary state of complex environments over time. An automated system that cannot represent its own uncertainty will project certainty, and that projection will be persuasive. The risk is not that automation makes mistakes. Every system does, but that it makes mistakes at scale while appearing calm, and that calmness invites further delegation. The deeper question becomes, which parts of the world are being rendered invisible by the demand for stable output, and which responsibilities are being displaced onto a mechanism that cannot carry them? Consider a single system you rely on, technical, organizational, or personal, and examine the boundary it assumes. Name what it optimizes, and name the proxy it uses to know it is succeeding. Then notice what the proxy cannot see, the inputs it treats as noise, the conditions it presumes will hold, the edge cases it has trained everyone to stop practicing. This is not a call to reject automation, but to clarify its shape. Reflection begins where the model ends, at the boundary where the system becomes confident for reasons that are historical rather than current. To examine that boundary is to examine the incentives that made it and the attention that now sustains it. When conditions change, stability can become a disguise for fragility.